Welcome to a discussion today about VSEPR shapes. How do we model the covalent molecules three-dimensionally? As we've been looking at drawing molecules, we have that inherent problem that we're putting two-dimensionally on paper something that's three-dimensional. And in order for you to get what you need from this unit, you need to be able to picture it three-dimensionally and get such things as the electron geometry and the molecular geometry for our shapes. So we're going to look at how they're actually arranged three-dimensionally today to help that sit with you. So you'll need out this list, our list with our central pairs, lone pairs, the electron geometry, molecular geometry, and a little picture. And I'm not so worried about the picture part. You need to be able to look at the molecule on paper, turn it three-dimensional in your head, maybe do some sketching on paper to help you, and then figure out the electron geometry and molecular geometry from that three-dimensional picture. I invite you to follow along with me today. So I have my little modeling kit. You can see that, yeah, I didn't spend a lot on it, and actually I like doing it this way because these work really well for our discussion. If you'd like to make yourself a modeling kit, which I would strongly recommend, you like to stop the video now, go gather some supplies, come back when you've got them. You're going to need 5 gumdrops for the center atoms, or dots in those yellow boxes. Work really well too. Something rather hard and sticky is what you need in the center. And then I'm going to use 20 white marshmallows, 16 colored, and 20 toothpicks. And that's what we need to model all of our VSEPR shapes all the way down through octahedral. Okay, so let's talk about how atoms function. So this is going to be my center atom, and here are 2 outside atoms. And so like these 3 are flying around in space, and they get close to each other. They start noticing with those electronegativities that they want to bond. Okay, and we know they're going to bond to decrease their potential energy. What would it take to hold 2 outside atoms to 1 inside atom, 3 atoms in total? Well, it would take 2 bonding pairs of electrons. So we're going to use toothpicks to represent pairs of electrons used for bonding. That's bonding pairs. So this is a bonding pair. On paper, I would draw a line. Actually, I think I just want some white paper here. There we go. I would draw a line on paper to show a bond here. So where do we put the other bond? Now I want to point this out. This is a bond. It's going to be a bond to another atom. Okay, so I have 2 atoms I'm going to bond to the center atom. Where should this other bond go? Okay, this is a pair of electrons, and this is a pair of electrons. Electrons are all negative. Electrons being negative always repel each other. And so what's the most these 2 can repel each other? They can repel 180. Now I'll have students go, well, what if I put that here? Then it's now 270. Well, yes, the angle is 270 here, but you've made it 90 here, and that's not going to happen. Like the magnetic repulsion is going to, no, don't put it there. So the furthest away we can put 2 bonding pairs of electrons. So I have atom bonding pair, atom bonding pair, atom. Furthest way I can do that is 180 degrees. So the bond angle there is 180 degrees. And so I look at this and I ask myself, how many pairs on the central atom? 1, 2 pairs, because remember, a bond is a pair. And then I ask, of those 2, how many is a lone pair? None of them. We only have 2 bonding pairs. So when I come to this chart, I see with a combination of 2 pairs in total, 0 lone pairs, it makes an electron geometry called linear. Yeah, notice how that's a linear looking molecule. Okay, and as there's no lone pairs, the molecular geometry is the same as well, linear. So there we go. We have our first shape is linear. If I'm holding together 3 atoms, maybe carbon and, well, probably not carbon. Let's go like beryllium. There we go. So beryllium and chlorine. It would make a linear shape, something like that. Okay. Now I'll point this out that VSEPR does not account for double bonds. So this also could be carbon, oxygen, and oxygen. This could be carbon dioxide, and they would be double bonded here, double bonded here. We'll talk about that in class, how you figure that out. But that also makes a linear molecule. VSEPR only counts the first bond, the sigma bonds. So beware. Okay. So I'm going to grab a new center atom because I'm going to drastically change shape. Now I'm going to be up to 3 bonding pairs here. So I'm going to bond to 3 atoms. Again, white marshmallows are my atoms. Okay. How can I arrange 3 bonds around a center atom in a way that maximizes the distance between the pairs, minimizes the repulsion? Well, hopefully you remember from geometry class that the furthest away we can have them, 3 of them, is to, take the circle, cut it into thirds, so 360 divided by 3 means 120. So a bonding of 120 there, 120 there, 120 there. And in theory, if I built it right, no matter which one I hold up, the other 2 are looking identical to that. All right, so here is what I get if I have 3 pairs total and 0 of them are lone pairs. So I go to my chart and see for 3 pairs total, 0 lone pairs, I have trigonal planar. That's what it's called, trigonal planar. Do you see a triangle? I hope so. It's flat. It all lies in a plane, so trigonal planar. Now on the AP test, if you say like triangle plane and not trigonal planar, that's usually okay. Okay, but it's a flat triangle, trigonal planar. And it has no lone pairs, so the name for electron geometry is the same as the molecular geometry, trigonal planar. Now I'm going to take this molecule and move on to the next one. I'm going to mess this up by, let's say, instead of an atom there, I'm going to put on a lone pair. And for lone pairs, I like using 2, because it's a pair, 2 colored marshmallows. So now I have bonding pair, and lone pair. Okay. So what have I changed? 3 pairs total around the atom, so still 120 going on. But of those 3 central pairs, one of them is a lone pair. So I go to my chart and I see 3, 1 still is trigonal planar. If I count all the pairs, electron geometry, it is trigonal planar. Molecular geometry ignores the lone pair. If I ignore the lone pair, what am I left with? Your sheet says angular or bent. Notice this is not straight. Do not say linear, you're not left with linear. Even though I'm ignoring, in terms of naming, that lone pair, the bonds that are left are not going to be straight. They are going to be angular because of the pair that's over here. So that's the difference between a molecular geometry name and an electron geometry name. Electron geometry counts lone pairs as well, all the electrons, whether they're bonding pairs or lone pairs. And molecular geometry ignores lone pairs and asks, what do you have left? Okay, so I'm done with this shape, and we're going to move on to the next one. And the next one's very interesting. I'm going to make 4 bonds. So I'm going to have 4 bonding pairs with 4 atoms. And how can I best arrange these around a central atom 3-dimensionally? I bet you already have it in your head. I'll stick one there. I'll stick one there. I'll stick one there. And I'll stick one there. Okay. Did you make something that looked like that? If you did, congratulations, you're wrong. And I kind of expected you to do that. I expect most students to get this one wrong. I know this is what it seems like, but you missed the fact that this is 3-dimensional. Okay, there's a whole other dimension available to the atom. So it's not going to be this way. It's going to be, and this is very tricky to make perfect, but you'll get the idea. And it's a gumdropper dot, so you can like redo it. It's going to be like this. So 1 always points up, and the 3 others point down into a triangle shape. Okay, this should be a little more down, I guess, something like that. Hopefully I'm getting it. No matter which one I point up, I should have some symmetry to it. The other should move into the place of the one that I'm pointing up. Okay, so this shape is tetrahedral. Okay, so tetrahedral shape. Tetra meaning 4 because I have 1, 2, 3, and on the bottom 4. 4 planes. If I'm connecting the white atoms here, I would need 4 planes to connect them on all sides. Tetrahedral, a 4-sided figure. It's all triangles. It makes a triangle pyramid with a triangle base. But that's tetrahedral. That is as far away from each other as possible. This angle everywhere between the bonds is 109.5 degrees, which is way better than the 90 degrees I first showed you. So this is what it's going to do in real 3-dimensional space. It's going to organize like this, tetrahedral. Okay. Now, I've not yet talked about polarity. I want to start talking about polarity. Okay. So I have a tetrahedral shape, and I want to know, is this overall going to be polar? So say, for instance, this is carbon, and this is, I don't know, hydrogen. Okay. Carbon is more electronegative than hydrogen, so it can pull on these electrons more. And it can, if this is hydrogen, it can pull on these. And if this is hydrogen, it can pull on these. And if this is hydrogen, it can pull on these. So it's pulling more than hydrogen on all of these. So it is a polar covalent bond here, and here, and here, and here. Would that overall make the molecule polar? Well, let's go back to an easier example before we consider this. Okay. Way back at the beginning, we had linear. Let's say this is carbon, this is oxygen, it's carbon dioxide. This oxygen's pulling this way on those electrons more than carbon. But this oxygen's pulling this way on those electrons more than carbon. So since they're equal pull in opposite directions, it's like a tug-of-war game on those electrons, and no one's going to win. The vector pull this way cancels the vector pull that way. There's no overall net movement of the electrons. So that means linear is nonpolar. And as long as you only have 2 elements, as long as it's not like NOCl, as long as it's just COO or something like that, BEHH, it will be polar. If you introduce a third element, then the polarity's gone. Okay, it's going to be polar with the third element almost every time, guaranteed. But if this center atom is different than the outside atoms, and the outside atoms are the same to each other, it would be non-polar. The pull this way cancels the pull this way, nothing happens, non-polar. Okay. Back to trigonal planar, we had originally with 3. So this is a good lead-in to our next one. You're like, if this is, I don't know, boron, and that's fluorine, fluorine, and fluorine. Okay. Fluorine's going to pull up this way. Is that pull balanced by anything? Well, no, it's got to pull this way and a pull this way. But if you view this as a triangle and it's pulling on the hypotenuse, we can really break that into a pulling on the opposite side and the adjacent side. And so there's this much pull downwards when I'm pulling in this diagonal direction. Does that much pull downwards cancel this pull upwards? No. But this much pull downwards from this triangle gets added to this much pull downwards from this triangle, and both of those added together, yes, it would equal the pull up. So it's a combined pull downward at an angle that cancels this up. And it's a combined pull this way at an angle that cancels this one. And it's a combined pull this way at an angle that cancels this one. Work the math out. It's just Pythagorean theorem. Throw a couple random numbers in. You should know the angles. And, work it out. Prove it to yourself if you need to. So this is non-polar. It's a 3-way tug of war. No one wins. Non-polar. No winner. Non-polar on the 3-way tug of war. That is assuming you have only 2 elements. This is some atom, and then these, and these are the same element. If these were different elements, then there'd be no way for it to cancel ever, and it would be polar. Now also we looked at with 2 lone pairs, Okay? Or sorry, with a lone pair, 2 colored marshmallows. Can an atom pull the same way an electron pair does? Well, that's actually a stupid question because an atom could pull. A lone pair, it's not going to pull on electrons, it's going to push on electrons. So this cannot balance this. And if those don't balance, there's definitely going to be a winner in this tug of war. The electrons are probably going to end down here. So this area of the molecule is negative. This area would be maybe a little more positive, or maybe the other way around. It depends on the molecule. Certainly with a lone pair here, this is more likely to be negative, I guess. So we have a negative side, we have a positive side, we have the poles of a magnet. This is going to be a polar molecule with that lone pair. No matter if these two on the outside are the same or even different, with that one lone pair, it's got to be polar. There's no other way for it to work out. So now we're ready to come back to our tetrahedral and ask, do these cancel? And this bond up does cancel by the combined three-way pull down. So each triangle makes a third, and third and third and third can cancel. So it is a combined downwards pull here that cancels the upward pull there. And it's a combined pull this way that cancels the pull this way. And it's a combined pull this way that cancels this way. And again, if you don't believe me, you can work it out with the Pythagorean theorem, and you should know the angles, and it's not too bad, really. So tetrahedral, provided this is one type of element and all these on the outside are the same, like maybe carbon and chlorine, 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 and chlorine, this would be nonpolar. They all cancel. Now let's change this shape. This was tetrahedral. We're going to change it by taking off a lone pair and putting on, wow, I said that backwards, taking off a bonding pair and putting on a lone pair. Okay. Now, would it matter which one I take it off of? No, because no matter which one I grab, it should all like have the same symmetry. Okay, so I just stuck it on the top there. Now let's talk about the name, because I have 4 pairs overall, but with 4 pairs overall and one of them being a lone pair, I now have, if I count it all, still tetrahedral. If I don't count the lone pair, what am I left with? Trigonal pyramidal. Notice how this is a pyramid, like that's the apex of the pyramid. So it makes a pyramid with a triangle base. Trigonal pyramidal. What's the polarity of this like? Well, a lone pair does not attract electrons like an atom does. So this would not be able to cancel. So this would be polar. So we have a polar molecule now with a lone pair. Now let's change this. Let's put on a second lone pair. So I'd pick any of the other ones, pull off that bonding pair, put on a lone pair. I just lost an electron. I guess I'm positive. Okay. Put on another lone pair. Okay. What can we say about this shape? Overall, still tetrahedral, but if I cover the lone pairs, what I'm left with? Angular or bent, not linear. And again, can lone pairs cancel out atoms? No. So this is going to be polar. Definitely probably have a negative on this side and something more positive on this side going on there. Okay. Now, what if we do, students always ask, what if we do a third one? Well, then we're left with just 2 atoms. That's got to be linear, so we don't waste our time on that. 2 atoms bonded together, doesn't matter if it's single, double, or triple bond, have to be linear. So, like, we don't spend time on that. We're going to move on to 5. What if we have 5 bonds around a central atom? I know I'm kind of building off screen here, because I want you to see it in all its glory suddenly. 5. How would you three-dimensionally arrange 5 around a central atom? Well, what they do is this. So I have 1 up, 1 down, and 3 that lie in a plane in the middle. That plane is a triangle shape. Okay, if I could like make a decent looking triangle. That's why I like using gumdrops. You can like readjust it. There we go. One up, one down, three around the middle that line a plane. By the way, we actually do talk about these like axial atoms and equatorial atoms, just to put some names to them. Not that that's anything you need to know, but that is how chemists refer to them. So what do I have here? I have 5 pairs around the central atom. 0 of them are lone pairs. So from my sheet, I can see with 5 pairs, 0 lone pairs, we call this trigonal bipyramidal. So let me show you this. I have a pyramid pointing up. If I'm connecting the white marshmallows, pyramid pointing up, a pyramid pointing down, and they both share the same triangle base. That's why it's trigonal bipyramidal. Triangle base, 2 pyramids, one up, one down. Okay, let's talk polarity because this is interesting. You're like, there's no way this cancels. Well, check this out though. This upward atom could, if it's the same, could cancel this downward atom. And then the 3 atoms around the middle can cancel each other like our earlier trigonal planar did. So this does actually cancel. This is going to be non-polar. There's going to be no winner in my tug of war game, so it's non-polar. Okay. We're going to mess this up. We're going to remove a bonding pair and add a lone pair. My question to you is, where should we put it? Let's keep in mind what's going on. This is an atom, and these are all electrons. And I'm going to put on electron pair instead of a bond. If I put on a lone pair here, it would be 90 degrees from everything. That's not bad, but check this out. If I put it on the side here, so again, 2 colored marshmallows to be a lone pair. If I put it on the side here, you're like, well, it's still 90 degrees there, yes, but it's 120 degrees on the sides here, and that is better. So this is what nature's going to do. This is the place of lower potential energy. Put that lone pair on the side. When I have that lone pair on the side, what's that going to do? Well, overall, it's still trigonal bipyramidal if I count everything. If I count all the electrons, the electron geometry, trigonal bipyramidal. What if I hide that lone pair? I have a shape that has a plane here, a plane up here, a plane on the side here, and a plane back here. So 4 sides to it, but those sides aren't all the same. So we call this irregular tetrahedral. 4-sided figure, but they're not all equal to each other, hence irregular. Okay. Now I say that, and then time and time again on the AP test, I see this shape referred to as seesaw. So literally, if you want to call it seesaw, I'm okay with that. This is why, like teeter-totter, seesaw. Like these would be the 2 pieces that hold it to the ground, and then the kids in the park can ride on each side and go teeter-totter, teeter-totter. So they accept on the AP test, at least they have in the past, seesaw, and so there we go. I personally like saying irregular tetrahedral because I just think that makes me sound smarter. And there we go. Okay. We're going to talk about polarity. Does the up still get canceled by a down? Yes. But does this cancel those? And the answer is no. There would be a definite winner to this tug of war. Someone's going to win. They're going to end up on this side or they're going to end up on this side. It would depend on the actual thing you're looking at. But there'd be a winner. So it is polar. By adding that lone pair, it's polar. Notice so far, adding lone pairs have always made them polar. Okay, we're going to add another lone pair. Notice where I'm going to add it. Again, for the same reason of getting it further away from the things that can be further away from, I'm adding it to one of those center ones. So now I have, well, I still have trigonal bipyramidal overall. But if I hide these lone pairs, I have what we call T-shaped, like the letter T. Okay, so T-shaped, if I put 2 lone pairs in the center, what we're left with molecular geometry is something that looks like a sideways T. I mean, you can tilt your head and make it look like a T, and then there you go. Okay, so T-shaped, what about its polarity? Again, the up would cancel it down, but these 2 lone pairs would not cancel with that atom, so this is going to be polar. Now we're going to go one more. We're going to add another lone pair. And for the exact same reason that I put the first two lone pairs in the middle, I'm going to put these in the middle. Okay. So what do I have now? I have one up and one down. Those are atoms. Bonding pair to atom, and then lone pair, lone pair, lone pair around the center. Okay. What am I going to do in naming this? Well, overall, it's still trigonal bipyramidal. Triangle up, pyramid up, pyramid down, sharing the same triangle base. What if I ignore all the lone pairs? What am I left with? A line. This is linear for molecular geometry. The bonds that are left without electrons counted are in a line. So it's linear. It's 180 between those bonds. What about polarity? Notice so far we have said with lone pairs that it's going to be polar. Here I have lone pairs, and this is nonpolar. Okay, these three lone pairs around the center cancel each other out because they're in an equilateral triangle, so they cancel each other out. And the atom up cancels the atom down, assuming these are both the same atom. If they were different elements, then it'd be all over. It'd be polar, as I've said many times. But this shape should be nonpolar because the lone pairs cancel and the atoms cancel. And so it's no winner in the tug of war. It's nonpolar. Notice we have lone pairs and even an odd number of lone pairs, and still it is nonpolar. So it has nothing to do with lone pairs. It's all about where are the lone and bonding pairs. It's their orientation that tells you whether it's polar or nonpolar, nothing else. Okay, one last one to model. We're going to put in 6. And if you've ever played a game of jacks, you have seen what it would look like to have 6 bonding pairs around a center atom. I've never understood the game of jacks. I'm like, why would you give little kids a ball and some pointy metal objects and say, here's a game, bounce the ball and try to grab as many of these sharp pointy objects as you can and squeeze them in your hand until your next turn? Yeah, I don't get that. But here we have 6 bonding pairs around a central atom. One up, one down, one left, one right, one front, one back. Okay, octahedral. I'd have 1, 2, 3, 4, 5, 6, 7, 8 planes to connect the white, 8 triangles, connecting the white atoms here on the outside. Okay, so octahedral. This happens. It doesn't happen often, but there are some elements that can get more than an octet, and this is one of the possibilities. If it's 6 bonding pairs, 90 degrees between all the bonds everywhere, doesn't matter which end is up, 90 degrees everywhere, it's octahedral. Now we're going to put on a lone pair. Should I put it on the top? Should I put it on the bottom? Should I put it on the left, the right? Where should I put it? I hope by now you've kind of realized it doesn't matter because it's 90 degrees everywhere. It's all equal. So it could be on the left, it could be on the bottom. I like showing it on the bottom, but could be on the top. Why do I like showing it on the bottom? Well, overall, it's still octahedral. Okay, but if I hide the lone pair for molecular geometry with 6 central pairs, 1 lone pair, we get square. These 4 on the bottom make a square, square, pyramidal. Okay, so there's my square base, and then they all connect to a pyramid up here. So square, pyramidal. Okay. So let's talk polarity. Can a lone pair balance out an atom? No, it's polar. What about when it was a lone pair? When it was an atom earlier? Well, that would have canceled, and that would have been then nonpolar. So I hope by now you've caught how easy it is to hopefully see the polarity, but you gotta see the polarity. You can't just memorize something to know if it's polar or nonpolar. These guidelines can help, but you gotta be able to sketch it and see it in your head, not rely on memorizing if it's this way or this way, then it's polar or nonpolar. Okay, last one we're going to do is to put on another lone pair, and this is important. I put it exactly opposite the first lone pair, because not only do lone pairs contain electrons that repel each other, lone pairs are physically larger around an atom than a bonding pair. So to get the physically larger things as far away from each other, regardless of the orientation, they're going to be on opposite sides. What do I have now? Well, octahedral overall. If I ignore the lone pairs, I'm left with square planar. The bonds that are left make a square shape that's flat. See how it's flat in the middle there? So square planar. What about polarity? We'll check this out. Lone pair up, lone pair down, they cancel. Atom left, atom right, cancels. Atom back, atom front, cancels. It all cancels. No winner in this tug of war. This is nonpolar. So again, we see we're back to having lone pairs, and it is able to be nonpolar. It matters the orientation. There's nothing to memorize to know if it's polar or nonpolar. You got to be able to do a little sketch and picture in your head what is the orientation. That's how you're going to know if it's going to be polar or nonpolar. Okay, so that's how we model our VSEPR shapes, that is three-dimensional shapes for covalent compounds. I hope this has been helpful in seeing how to read the polarity, because that's not on your chart. You got to know how to figure out the polarity. So you'll use your little sketch to figure out how many central pairs, how many of those are lone pairs. That will match you up a electron geometry and a molecular geometry, and then it's up to you to tell me about the polarity and hybridization. Thank you for your time. Good luck.